Hi, welcome to LMS solution. Today we are going to see about MATLAB simulation of Zeta Converter for the BLDC motor for power factor correction. This is a simulation model for Zeta Converter for BLDC motor. It consists of AC source, single phase AC source, and then is going to be converted into DC by using a diode rectifier. And then here we are using capacitive filter to convert that full rectifier output into DC. PDC. After that, we have used theta converter here. This arrangement known as theta converter, and theta converter output going to be connected to the voltage source inverter and the BLDC motor, and the BLDC motor going to be controlled by means of Hall sensor position. Hall sensor position going to be converted into yielding pulse by using this arrangement. The pulse going to be given to the voltage source inverter to control the speed of the BLDC motor. Here we are going to use, we will implement power factor correction circuit. Why we go for power factor correction? Because here we are using a diode rectifier, this one. Then we are going to use this diode rectifier. What will happen? The source current, the nature going to be changed. Normally, directly you are going to use this AC supply to drive the any AC load. The current will be sinusoidal. When we are going to use this kind of load, going to be considered as a non-linear load. That means diode rectifier is going to be considered as non-linear load. So when you are going to use this non-linear load, what will happen? The nature of that source current will be is non-sinusoidal. You will get this kind of waveform in the current. We need to make this nature of this current to sinusoidal. For that, we go for a power factor correction circuit. How we are going to apply that power factor correction circuit, we will discuss here. Here we are going to apply two loops. One is output voltage control, that means voltage control in the Zeta converter output end. So you have to control this output voltage of the Zeta converter, and then we are going to use current control, the current controlling of that diode rectifier. We are going to control the diode rectifier current in order to make that source current to sinusoid. So we are going to apply two loop. One is outer loop used to for control the Zeta converter output voltage, and inner loop going to be used for control the current of the diode rectifier, not to make source current sinusoidal. Further, you have to measure VDC here. To measure that VDC, that means output voltage of that Zeta converter, and then we're going to compare with some reference voltage. Here we are taking reference voltage is 250. After 2 seconds, it goes to 150. So we are going to compare with that reference voltage. After that, it's going to be processed via PA controller. The PA controller will generate some reference current magnitude. So this reference current magnitude is multiplied with some sinusoidal waveform. So the sinusoidal waveform, here we are getting sinusoidal waveform with the amplitude of 1. That can be generated based upon source voltage. That means here we are going to measure the AC source voltage. The AC source voltage is going to be processed via PLL, and then it will be provide omega t. That omega t can be processed via sine block. Here you will get the sinusoidal wave. After that, the sinusoidal waveform going to be multiplied with this controlled output of the PA controller. That means current reference magnitude. Here you will get a current reference in sinusoid. After that, you have to use absolute block. So this absolute block going to convert the nature of the reference current to like this. You will get this kind of, that means it's like the full wave rectifier. Same way, this is going to be reference current now. Next, you got to measure the diode current here. So here we are going to measure the diode rectifier current. The diode rectifier current once again is you have to apply absolute value. That means you have to convert a negative portion to positive. Here also you will get some positive response here. That means we are going to convert that current diode rectifier current to, that means we are going to convert the negative portion to positive. We always get only the positive portion of that diode current, right? Diode rectifier current. So next you have to compare this reference current with this diode rectifier current. Then it's going to process via PA controller. So the PA controller will generate the duty cycle. The duty cycle is going to be compared with the triangular wave. The triangular wave generates the pulse, dual impulse for that IGBT of that. This pulse going to be alter the nature of this diode which rectifier current. It going to be change the nature of this diode rectifier current to the near sinusoidal. Because of changing this current nature, it also going to change the current nature of this source current. So this is the working of the power factor correction circuit. Here we are going to measuring the power factor of the source. That means here we are going to measure the source voltage and source current, and then here you will get the power factor of the circuit. This is the source voltage and the current waveform. In this scope we can see that source voltage and source current variation, and then in this scope we can see the variation of converter voltage, that means Zeta converter voltage and the output current of that converter. So here you can see the stator current and the stator back EMF for the BLDC motor, speed of the BLDC motor and torque of the BLDC. So I am going to simulate this model. Here you can see that this is source voltage and then source current. Both will be in phase, and also you can see the nature of source current is sinusoidal. And here you can see that this is the converter voltage, and then this is converter current, and then here you can see that this is speed of the BLDC motor, this is the torque of the BLDC motor. This is a power factor. You can see the power factor maintaining at around 1. This is stator current of the BLDC motor, and then this is EM of the BLDC motor. We can see that the nature of source current is always sinusoidal. Power factor of the source going to be maintained at unity, and also you can see that the initially that reference voltage is around 250 volt. Now we can see that it comes to 250 volt. The voltage regulation also going to be happen in the system. So here we are going to control this voltage of the converter output voltage. This way we can control the speed of the BLDC motor. After 2 seconds, the reference voltage will be changed from 250 to 150 volt. Right? We can check the variation of the converter voltage, and also you can check the source current nature. At the time of 2 seconds, the reference voltage changed from 250 to 150 volt. We check the response of the converter, and then the nature of the source current. Now we can see that because of changing reference voltage, what will happen? The voltage is reducing towards to that 150 volt, and also you can check the current nature. Current nature is maintained at the sinusoidal. Here also you can see the power factor is reducing to 98 and then 0.96 during changing reference voltage, and then it's once again going to rise it here. Power factor we are changing. We will check that after the voltage reach to 150 volt. Here now we can see that the power factor is increasing towards to unity, and also you can check the nature of the source current is still sinusoidal, and also the phase angle difference will be 0 between source voltage and current. You can see the power factor goes to nearly 8 duration, and you can check the nature of the source current also sinusoidal. For changing reference voltage also, the power factor is maintained around unity. Now after 3.4 seconds, we are going to change the load from 0 Newton meter to 0.5 Newton meter. We check the result after changing the load condition. What happened to the power factor and then source current, everything you have to check after 3.5 seconds. Now the load going to be changed from 0 to 0.5 Newton meter. Now we can see that because of changing load in the BLDC motor, the current of the converter will be changed from 0.3 amps to 0.8 amps. And also you can see this because of changing load, what will happen? The voltage will be comes down and then go back to the track the reference voltage here, and then you can see the source current. The source current is still sinusoidal, and also the power factor is around only unity. That means the phase angle difference between the source voltage and current is 0. That's why the power factor maintain unity. And also you can see that after changing the load condition, what happened? The voltage come back to the reference voltage. That means it's nearer to 150 volt. For a change in reference voltage as well as change in load condition, the system maintain that unity factor nearer to unity, and also it track the reference voltage command, and also even the sudden load changing condition, the power factor also maintain unity. Thank you. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much.